So, my topic is misadventures with the data. Almost 10 years back, when I went to my postgraduate, I was handed over the topic of thesis to me, and it was said that go out and figure out yourself. The first question that came to my mind was, should doctors learn statistics? Uh, what is important here is to know that the first p-value was calculated by a physician, Scottish physician, John Arbuthnot, and he determined the difference between male and female mortality rates in England. Daniel Bernoulli, the famous physician who later turned mathematician, did lots to probability. The next debate is consumer versus creator. I personally think when the stakes are high, we should always bring in a statistician in a debate. For example, if we are doing trials and everything, but we do read the trials and we are the consumers, so we must know how to interpret the data and not caught in dichotomies. Unfortunately, what happened after 1990 was a good time. EBM movement started. But then somehow in the timeline, what happened was people became flushing out too much research, small trials, underpowered trials, and research work became an alibi for showing off your intellect or, as a matter of influence. And that decreased the effect of our clinical judgment. So the important need is for critical consumption. Most of the media releases tend to dichotomize. If this result is significant, they will report it as positive trials, irrespective of the effect size. Or if the result is non-significant, they will report it as negative trial. That is that, and I will give you examples of the same. So somewhere, the distinction was lost. I am a Bayesian. That is, I think that the randomized control trials are the best way to look at relative efficacy of two treatments. But then we reserve that right to interpret the data, and we should not be bounded by the limits of significance and non-significance. So one of the most important things a clinician can bring, apart from many things, is to look at the demographic table of the data first, of the study first. That is where we can, criticize or look how representative the data is. In common sense, we bring the clinical significance back into randomized controlled trials. If I had to rename it, the talk, I would rename it as bringing clinical significance back. So first, when 10 years back, when I was conducting my first, when I was given my first topic, so I was confused. So one of my seniors handed me this paper. One second. This algorithm of that this is how you analyze the data. If the population is one sample, you do a one sample t-test after checking for normality. Two sample, paired or unpaired, you must have seen some variants of it. A lot of it is wrong. You cannot do a simple statistical test. You can do, but the test is not sensitive enough to check the distribution is normal or not normal. One. Repeated measures one way ANOVA is not the best way to do it between pair samples. Ironically, my study had both of these. I failed at testing for normality and repeat measures one way ANOVA, but I conducted the statistics anyway. I mean, this is the way we learn. We make mistakes and we learn. My advice to the people who analyze or collect the data would be first to visualize the data. I hope you can look at this now. So you can look at this datasaurus, right? All the data points have a correlation of minus 0.06, and yet you see how the data is looking. Sometimes it is linear, sometimes it's in the form of a dinosaur. So that is why it is important to visualize the data. For same correlation, you might have a different mean or different standard deviation, the same correlation and same even standard deviations of some variance. You can have all things similar, but still visualization is utmost important. You look at difference between a relation between human development index and corruption in this slide. You have an R of 0.457, and yet you'll see how the data is behaving. Initially, with rise in human development index, the corruption rises, as has happened in India or in 1930s America. But when the systems became mature, the corruption falls. And yet, if you looked at the data, you would assume it was just a negative relationship, right? So that is why visualizing the data is of utmost importance. This is the Anscombe quartet of the light, speed of light, which were used by Einstein. Again, you see the data all have similar correlation and similar R square, and yet the data is totally different. That is why there are two assumptions, though two important things. One, the data is not always linear, and second, you don't trust the summary statistics first. You ought to visualize the main variables that you are analyzing. That is the first lesson, which I have learned after making a lot of mistakes on the way. Again, some general points. You should avoid pie charts. We should use box plots rather than just bars, because bars won't convey standard deviation or how much the data varies. And we must learn how to interpret them. If possible, if we have fewer data points, you can use interactive graphics, as in we know every data point, what it is ID is, or what it, so that we can visualize exactly which patient has this wildly off data point or wildly off or not. Then we can use panel plots. These are small plots showing various relationships with respect to 3 variables or so. Now coming to design of the studies. This is also my pet peeve. Frequently, you will see that the power of a study and sample sizes are made according to the convenience. So what will happen is people will choose a avoid point estimate from previous studies. Like say, they will say that this drug had 30% or 40% reduction in mortality rate, and they will power according to that. Now, this is clearly leading to underpowered trials, right? So inconclusive estimates, which will be branded as negative trials, as they fail to reach a conclusion because people are obsessed with negative and positive and not concerned with effect size. The other point is, but if you are constrained, many times we are constrained for resources, then we would advise to use continuous parameters. For example, Orbita, a great double-blind trial of sham versus measures versus PCI in stable angina. So they didn't do an event trial. They powered it for time to angina on exercise test, and it was a very good trial. So Stephenson, the famous statistician, advises that you should always use a continuous measure if you are constrained for resources. Okay. Of course, there are risks of surrogate outcomes, but that is why I'm a fan of people collaborating rather than dishing out underpowered trials for various regions, for publishing, for primary authorship. Now, Orbita, a good trial, was criticized that it has only 200 patients. But you must understand that in continuous parameters like time to excess angina, so the sample size will be small because it is continuous, while in event trials like death or hospitalization, even you will have to take larger number of patients because the deaths will be low. And that is why clinical effect, that is important. What effect you generally think? From the data by Ioannidis, and generally maximum studies tend to have risk reduction between range of relative risk reduction between range of 0.5, that is 50% reduction, to 50% increase. Generally, that is the case, or at maximum from 0.3 to 2. So we must know that in real world, there are no miracles. Only a few drugs will be very good, and most of studies are small. So it is good to be skeptical, as we have seen with many medical reversals like stop sepsis or insulin in ICU, which happened in low sugar trials, which happened in 2000 to 2010, the decade of reversals, which has been made famous by Vinay Prasad. So it is good to be skeptical. And also, Ronald Fisher, the famous statistician, advised if you are, going for a bigger haul, it is good to consult a statistician at the design stage. So I think that is a good idea, because you can anyway, if you come take the data, you can always get it analyzed somewhere later, or you will get some help. But it is at the design stage, it is most crucial, and that is where we tend to avoid the statisticians. I mean, it is not that they are the greatest, but since they have done so many trials, or if someone is a genuine statistician, he might have worked and he knows the flaws. So it is a good idea, one, to collaborate, and two, to take help at this stage if you are in a bigger gun. And in fact, what I generally look while critically appraising a study is I look at the power calculations first. Where the point, was the sample size unrealistically calculated? And I will get to it in a minute. Other thing is dichotomania. What is dichotomania? Let's suppose, and this is pretty common, that is, except for death or non-death, which is a real dichotomous point, many things are made dichotomous. Example, a patient, suppose a drug, paracetamol, causes a headache reduction in all of the patients, right? And we arbitrarily divide headache improvement at 2 hours, right? So only 59% of people are getting a response in paracetamol group and 48% in placebo group. Whereas the fact is, it is happening everywhere. For each headache, it is reducing by 3/4, right? So we will arbitrarily make a conclusion that only 10% of the guys are benefiting. So that is the wrong thing to do, right? Here we engage in dichotomia. In fact, I did the same thing in one of the trials. One of the trials I was involved in, we had the acute asthma cases, and we arbitrarily divide the result, the improvement in breathlessness at 2 hours. And it was an arbitrary, but it was supported by GINA guidelines. But it is an absolutely arbitrary and, I guess, a foolish decision to make. And the sin of dichotomania, arbitrary division, coupled with NNT, will lead to another disaster, which I shall be talking about next. Now, coming to appropriate summary statistics. See a famous politician, I mean, son of a famous politician, rather controversial, I should say. He's confusing between mean and median. Now, we know generally mean is confused by outliers. Mean is affected by outliers a lot. I generally prefer median or interquartile range, unless until there are too many tiles. Mean is good for normal distribution, but it is true that most of the parameters, many of the parameters don't have a normal distribution. So except for the ties, people, if the data doesn't have too many ties, I think medians are the best. Appropriate descriptive statistics. I mean, people should always quote full p-values and give the confidence intervals. The second thing I'm fond of, rather, is relative risk and odds ratios are maligned. Example, you can always calculate absolute risk reduction from a relative risk. For example, a person has a baseline event rate of 5%, right? And some drug causes a relative risk reduction of 30%. So 30% of 5%, that is 1.5%. Okay, so that will go down to 3. In the experimental group, that will go, the event rate will go down to 3.5%. So there will be absolute risk reduction of 1.5%. And if the rate was 60%, the control event rate was 60%, the rate will go down by 30%. That is the decrease of 18%. That is absolute risk reduction. But suppose someone in trial gives you only an event rate, the absolute risk reduction was 5%. But so you cannot extrapolate it forward, right? And inverse of 1 by absolute risk reduction is number needed to treat. So number needed to treat was, dumbing down of medicine. Why I say that? Because from NNT, you cannot calculate relative risk, which will be relevant to your patient, which you are seeing, but it might be good epidemiologically for patient on the whole, but for the patient at bedside, relative risk will be better. Now I'll be talking about non-parametric tests. Non-parametric tests are tests which don't assume a normal distribution, right? Which do a hypothesis. If you are interested in hypothesis test only, that if this thing works or not. Now, suppose a group A has a creatinine values of 1.1, 2.2, and so B has some values, a higher set of values of till 10, and group C has all the similar values except 10 is replaced by 30. Some very heavily muscle mass and patient with ESRD with an outlier. And when you run the t-test, so A versus B, okay, it is significant, but A versus C, where the creatinine is 30, the significance, it is not attaining significance, while the non-parametric tests hold as good, right? As I told, that the tests of skewness are not sensitive enough, right? So non-parametric tests are robust, they are sensitive, they are good with outliers. So I think you should always do a non-parametric test for sensitivity testing. Is your data, is your thing robust enough? Are your conclusions robust enough? I call number needed to treat, number needed to mislead. And Stephenson, the famous statistician, calls it so as well. So again, coming back to the example. So paracetamol, as I was talking about, let's assume this simulated population in which paracetamol reduced the duration of every headache by 3/4. Then when we arbitrarily make the improvement of headache at 2 hours our goal, this thing is reduced to 59% and 48%, and the difference is around 11%. So we conclude that only 10% with tension type headache, that is 1 by around 0.1, that is around 10, that is one in only, that only 10% people with tension type headache will benefit from paracetamol. Whereas the truth is every person is benefiting, right? There you saw the irony of it. Not firstly, we had the sin of dichotomania, which was driving out a wedge at an arbitrary time, and then the number needed to treat is just calculating this difference and leading to assumption that only 10% people are getting benefit from paracetamol. And this actually appeared in a Cochrane review. And this is a graphic by me, which was inspired from Sen, which clearly shows that. Now, again, which I was talking about, consider a hypothetical trial with a hazard ratio of 0.6. So if the baseline hazard rate is high, right? So your absolute risk reduction will be higher, right? And number needed to treat will be lower. While absolute risk hazard rate will be low, then absolute risk reduction will be low, and number needed to treat will be higher. So that is what is important. People will, and a few days back, what happened was, and comparatively in cancer trials, what frequently happens is you will give the drug to a sicker group of patients, and though they will have increased absolute risk reduction, but since their life is prolonged, since their life is short, the median improvement will be short as well. While in trial, where generally what happens in trials, in randomized controlled trials, you have healthier patients, so their median improvement will be higher, right? Because the baseline hazard rate is low, even though okay, while in the patients with higher hazard rates, though the improvement, the absolute risk reduction should be higher, but the patient has lower lifespan, so your lifespan will be lower. This observation was criticized by an oncologist on Twitter that say that real life trials are not translatable to real world, when the actual conclusion is wrong. You should have been using hazard ratio. It is expected. So that is one way we can use that as point of care. Then clinical significance versus statistical significance. Now, every one of us knows this point. Every one of us have been emphasized, and yet I shall demonstrate to you how it has been misused, or we tend to forget it again and again. Now, we all know, right? This is how we do. This is a risk ratio. This axis is of risk ratio. The risk ratio of 1 means that both drug and placebo are equal. If the drug will cause 15%, if the drug will cause risk, and this on the left of it, it is in favor of the drug, and on the right of it, it is not in favor of the drug. It is favoring placebo. So let's assume a clinical significant difference of 15%. Normally, what we say is you can, and this can vary, right? According trial to trial. For example, if you want to implant a device, generally we take at least drug should have a 15 or 20% decrease in event rates. While for a simple, let's say, drug like tranexamic acid with no side effects, even benefit might be 5%. That should be clinically significant, right? Or even 6%, or even, I mean, that may vary from case to case, and that is where our clinical judgment should come, where absolute risk reduction and what amount of the risk reduction is important. So let's look at the trial A. It is clearly statistically not significant, but it is lower than what we want to achieve, at least a risk reduction of 15%, right? Suppose a drug has certain costs. So this drug is statistically not significant, and neither is clinically important because it is not able to improve on our at least the minimum quality which we demand. Then A to B, statistically not significant because it is crossing the 0 line, but maybe clinically important because it is crossing that clinical mark. It is still non-significant. Then C, it is the zone of equivalence between 0 and the minimum clinical. It's statistically significant, but actually not clinically important, right? Here, it is both statistically significant, but since it is crossing, it is maybe clinically important because it has just crossed the boundary of minimal clinical significance. And here, E, that is statistically significant and clinically important. Now, I was emphasizing it because this mistake we tend to do a lot. Sometimes many trials will fall into this, yet the pharma companies will tell us that they worked. While many times your trials will be falling in this range, and people will be telling that treatment doesn't work, where it may be clinically important. That is why Stephenson, the statistician, advises us that the trial should be at least powered that so and so that they shouldn't have this range in between, right? They should be powered so that they don't miss at least this clinical difference. So the delta difference which we use in sample size calculation should be at least the difference we don't want to miss, because what happens is if the trial is negative, that is, it doesn't reach significance. So what generally happens is it is branded as negative, so it loses its chance. So this trial is absolutely fine, A, because it shows that this drug is not achieving statistical significance. Okay, that is okay. But B, it still leads to a lot of loophole because it can still exceed A value, right? It can still exceed a risk reduction of 85%. Okay, an risk ratio of 0.85. These are the clinical examples of trials, that is aspirin versus VC, aspirin versus placebo. These are from some meta-analysis. We just have to look at risk ratios, right? Let's assume an event rate of relative risk reduction of 10% as clinically significant. Then we see aspirin versus placebo. Clearly, it is clinically significant and statistically as well. Here, what we see that it can go all range for 44%, that is almost 56% risk reduction, to around just clinically, it just crosses significance. So here, what is happening is this might be clinically significant, but it is non-significant. Here, again, this might be statistically significant. This is statistically significant and may be clinically significant as well, because it is crossing our arbitrary borderline range of 0.85. Here, it is between 0.86 to 0.99, so that means it is statistically significant but not clinically important, right? While we see that is 0.86 to 1.06, it is statistically not significant and clinically not important, right? So now coming to p-value is not the level of evidence, and yet people tend to confuse the two. Let's see that. So p-value, let's say you see that number of patients receiving, suppose a patient number of patients receiving both A and B is 20, and 15 are receiving A and 5 are receiving B. And the numbers change and all have the same p-values, right? While in one, the difference here is statistically significant and not clinically important. While in other, it might be clinically important. That is depending on confidence. So p-value is definitely not the marker of clinical significance, because CE, right, the difference is very minuscule. As we know that if the sample size increases, very minuscule differences will also come out to be statistically significant. So that is why P cannot be relied. That is why all the EBM people have advised generally relying on effect size and confidence intervals. Now, this is easier said than done. Because people are often caught in dichotomy, and that is why I call this a call for Bayesian statistics. Let's see this tweet by Professor Darrell Francis. He ran a famous tutorial which has over 2,000 votes, around 1,700 votes. What does P.03 mean? Now, the real chances, real probability. Okay, if the drug is ineffective, that is 3% chance that produces an effect significant, right? So the C was the correct answer, and D, 3% probability this drug is ineffective. That people assume. Actually, people are Bayesian. They think that it is the probability that drug is ineffective, which is not. P-value is not the base rate, and most people tend to confuse the two. Despite on Twitter, so many scientists are there, and many people confuse the two. And this difference is important because this has led to a crisis in statistical research. This is a question in an exam I wrote. This is AIMS, famous exam in India. They use postgraduate. There have been variants of it where at least the AIMS tests upon the EBM, they regularly confuse a p-value with a base rate, right? That only non-significant 1% of time. It is a wrong assessment, and this question has been tested many times on the AIMS exam. It means even our testers, people who test the exams, have wrong concept of p-values, and that goes on to show that p-value is like a religious commandment. Most people know it, use it, but what they think is clearly different from. They tend to confuse it. In fact, if we really want to calculate what is the base rate, that is the non-significant or the significant rate we have to use base, right? Bayesian value, Bayesian parameters. What the Bayesian value, Bayesian statistics wants you to assume a prior distribution. Now you will say that it sounds very complicated for me. Actually, it is not. We generally know from our clinical experience that most of the drug sizes, effect sizes are small. That is relative risk from 0.5 to 2 or maximum from 0.3 to 3. And then we put on the data and then can calculate what results come after the match of the prior and the data. In real life, what I really want to know, I'll go back a bit, is what is the percent chance I will have a clinically significant difference rather than just looking at visually. Or I will want to know what is the percent chance that my drug will have effect between 15% to 0% reduction. Or I will want to know that what is the percent chance my drug is truly inferior. And these calculations can only be done by Bayes right? So that is why Bayesian statistics is important. While you can make that judgment also visually, Bayes gives a number. It is also possible in frequentist statistics with equivalence test, but it is a bit difficult. So that is what I was talking about. We are really interested in how much a drug has chance, how much a drug has chance to cause a benefit that is greater than a certain minimally clinically important difference, minimal clinical or clinical significant difference. So that is how you assume. You assume a prior distribution, right? Then there's the data, and posterior distribution, we match something between prior and data, a match of prior and data. Now, Bayes hypothesis testing that drug works or not works can also be calculated by Bayesian methods, that is Bayes factors. That is different from the percentage calculation I talked to between. It is the difference in heights of posterior and prior at null hypothesis, that is size of zero effect. So it can be calculated, and it has significant advantages, as I will demonstrate. So a call for Bayes. So Bayes not only allows Bayes factor is also level of evidence. Remember the p-value I told you? That p-value is not a measure of evidence. If you have a high p-value of 0.9, it doesn't mean that the drug doesn't work. It might as well that Fisher said that if your p-value is very high and your sample size is low, this thing is calling for more data. This experiment is calling for more data, and yet people tend to confuse. The high p-value means the drug doesn't work. At the same time, I showed that a low p-value might be achieved in a very large sample size trials. So that would not help as well, right? So it is not a measure of this thing. Most of us interpret confidence intervals already in a Bayesian sense, right? So most of us assume that confidence interval is this, so drug generally the mean effect is between this and this range, right? But this is a Bayesian interpretation. So you might ask, but I generally do it, but then you should use a Bayesian method as well. As I said, that I want to know that new drug is superior, truly inferior, or in zone of equivalence. That is what is clinically relevant to me. And then can be used to calculate utilities. That probability of death is this much. We multiply the utility of death in composite scores. And if you are really skeptical, as in happens in multiple comparison tests, you can use a skeptical prior that suppose, okay, I assume since it's a nutrition trial or it's an observational study, it is most likely the benefit will not be large. Relative risk reduction of vitamin D in mortality think could be maximum of 10% or 5%, and you can accordingly adjust the results for your clinical interpretation. You cannot do it in p-values. And think about it. Most of the nutritional research is of poor quality, and you can do a skeptical prior. You can also use a skeptical prior for secondary endpoints, and like multiple comparison and multiplicity testing. Frank Harrell, the statistician, has written a famous blog on this you might read. So that is what I was talking about. Sometimes your prior would be neutral, right? 0.5 at base of 0, it can go to 50% reduction here to 150, almost a relative risk of 2 here. Sometimes your prior might be enthusiastic, right? And sometimes your prior might be skeptical. That is a low, a low chance of low effect. So that is why you can do a sensitivity analysis, and that is the advantage of using Bayes. Now you might ask that it appears very tough for me. Actually, I used to do the calculations, and I have coded a web app. So that you can use it for your clinical presentations. Once again, looks like my audio is lost a bit. One second, let me figure out. Okay, So I assume I'm audible again. Okay. So the Bayesian. Okay. So I got back again. So the Bayesian inference. So I coded this web app.
Okay.
Okay. So I coded this web app. You can actually look at, you can input the number of variables, the minimum, the expected risk reduction, what you can use your custom priors, and what minimal clinical significant difference you assume, and what is the your importance, what is the range of your equivalence, and you can calculate these values. So this is the way in which it can be done. And you can do the hypothesis test on this site, medstats.adspace.cc.evidenceofabsence.html, by this method as well. So you can use ifrequent. These methods are not complicated. I'm having internet connecting issues. 1 second. Sorry. Okay. I presume I'm audible again. Arvind? Hello? Am I audible? Okay. So the next question, what happens is frequently inconclusive trials are classified as negative RCTs. That often happens in practice. That I'll give you an example. Here, an odds ratio of example, and I see it frequently in Twitter. You see an odds ratio of 0.92 to 2.16 was classified as being a negative trial. So this was a famous trial that ketamine in RCT, which is ketamine is in brain injuries is harmful or not. So despite the trial showing such, they said that okay, the odds ratio it is non-significant, so it was branded that ketamine is not harmful. Well, this thing we see that the clinical it has truly the alternative option is better. In hypothermia trial, it was inconclusive, yet on Twitter it was said that okay, it is negative trial, non-insignificant, but still, so it doesn't work. In Ebola trial, a trial with high case fatality, we have a high risk reduction of around 40%, and still it was branded as a negative trial, even though the significance is large, right? Even though the range confidence intervals are large. In levosimendan, the same story. While you see in a trial like Predimed, which is nutrition research of Mediterranean studies, right? Though it has reached a very high statistical significance and clinical significance, we know by our experience that unlikely nutritional research studies are unlikely to be that high because the biological plausibility didn't work out. So we should apply a skeptical prior, and that is what happened. The Predimed study was retracted and published again. Then a meta-analysis, again, this was in PFO trials. PFO trials, we saw the PCI, the PC1 and closure trials, which were inconclusive and thoroughly underpowered. And it was showing no difference, and yet they were concluded as negative trials. While Respect 13, which showed an evidence in favor of PFO closure, though it didn't achieve significance, right? It was branded as negative trial, even though it clearly appears that it is crossing the line of significance, that is almost 10% reduction by far. So these are examples. Fortunately, base factors help us calculate. For example, look at this equivalent, statistically significant trial B, but equivalent. Here, the base factor is 0.51, that is favoring the null hypothesis. Base factor against, that is a base factor against alternative hypothesis, though the p-value is significant. So that is why base factor has a continuous line of evidence, unlike p-values. I generally advocate using the effect sizes and the absolute and the risk reduction equivalence percentage. But the base factors, if you want to do hypothesis, you can do the base factors. Let us look at the meta-analysis. The early renal replacement versus delayed renal replacement. Again, what is happening here? Here we see that the real dependence and the survival, here the confidence interval is large, 0.41 to 1.44. So the evidence here is inconclusive, and yet it has been branded as if that we don't have any evidence as yet, and yet many people have confused this confused this inconclusivity with negative trials. Similarly, the pharma reports, again, here you have all statin sizes of primary mortality. Again, the effect sizes are nearly similar, whereas the lines in media, the trials which cross the line of significance are branded as negative, while those which cross the line of which don't cross are branded as positive. So that frequently happens. Then, similarly, in a study of oral anticoagulants, the same story in dabigatran versus apixaban, right? So it is all about, even though effect sizes are small, I'm taking these examples from the media releases which commonly occurred. Again, the varenicline example. While the Singh trial, which showed that clearly varenicline has higher risk of cardiovascular mortality, but yet in a Prochaska trial, though the effect size was similar, it was branded as non-significant. A negative, that it doesn't have more negative side effects just because it crossed the line of significance, where the effect sizes are roughly similar. Again, in PCI, left main disease, again the same story. And you see the meta-analysis are also doing the same mistakes because they are underpowered by small studies as well. So you have a broad confidence interval. Generally, for me, a confidence interval to think that it is inconclusive should be of a lesser range, like 0.8 or 0.9. Here you have all the way risk reduction from 34% to a risk increase of 34%, 24% to 34%, and they are branding the trial as negative. I mean, both things are equal. Clearly, they are not. Clearly, they are not equivalent. Again, this was another trial, same story, 0.72 to 1.40. It has again been branded as equivalent when it is clearly not the case. Then there is a story about composite outcomes. Frequently, your trials will have a composite outcome where the important measures will be combined with non-important measures. For example, death is more important. Your validity of individual component, you have to justify in your composite measure. You have to avoid clinically unimportant, and you have to ideally weight all of them. For example, death is most important. Frequently, the trials are hacked, as in a clinically non-important measure is attached, because it is not possible to weigh components prospectively unless you are a Bayesian. So that is what it is. So you tend to report the components separately. So this is the frequent way in which the mega trials are faulty. Then a call for models. Let's look at a famous trial, Orbita. Here we had the trial of PCI versus placebo. And we see that both drug groups were controlled. The P was non-significant, it was balanced. And yet people attacked it because the pre-randomization exercise time was slightly higher in PCI, rather than placebo, right? So, so they said that PCI had already a large good group and it was unlikely to benefit. So what if so it would have been good if in a regression study they would have taken this along with other regression variable, that is analysis of covariates, and that is what was done in second orbiter study, where the effect size was more precise, though it still came out to be non-significant and showed a less effect size. So that these mistakes can be avoided if you ask for analysis of covariates and avoid change scores. Frequently, change scores are used, that you use one group at start, then the baseline, and then you subtract the two, then you compare it from other groups. Then analysis of covariates is better. If you are not doing it, you should ask a statistician who is consulting you. Again, this simulation in R shows that the t-test is similar to a linear model. So it is not as if it is conceptually similar. Now, regarding diagnostic studies, sensitivity, specificity are backward probabilities. We generally need positive or negative predictive values. And why should indeed a test should be a marker for positivity or negativity? We should combine all variables. We should have other covariates and prognostic models. And that is how it is useful. But to take a test in isolation is not good. Also, work of bias can change the sensitivity and specificities. So they are not invariant like odds ratio or relative ratio. And hence you shift from AUROC to a better predictive accuracy score like R square or C stats. So this talk was mostly a nudge to understand things better, or which I did wrong. I think there are some resources like JAMA Users Guide, Frank Harrell's blog. For visualization, you can use Plotly. For open source software, point and click, you can use JAS and Jamovi or R, while you can use Twitter for journal clubs, as is done. So I think these are some useful resources that I want to talk about and my experience with stats. Thank you.
Thank you, Dr. Anupam Kumar Singh. That was an excellent briefing on statistics and the use of statistics in medicine. If any of you have questions, the audience, can you please raise your hand or type it out on the app itself, and I will ask that question of Anupam. And to kick off, Anupam, we have about 5 minutes left. You talk about underpowered trials, not enough numbers, and so on when you are looking at significance, and maybe things are not getting to significance because of underpowered trials. Mm-hmm. Is that because the numbers are not enough in such trials? In any case, when you start off a trial, there are formulae to calculate the sample size. So what actually goes wrong?
One, what happens is obviously there is a crunch of resources. The numbers are not enough. So people generally decide that they take numbers in advance and can do the retrospective calculations of sample sizes. I mean, this is unethical, but frequently happens, as every statistician will tell you, right? So that is why my advice is to collaborate. What has happened in publish or perish culture, people are doing individual research for primary authorship. So people don't tend to collaborate because they don't get to get credit. A sample size formula will also only act for the value which you have been put in. So example, if you power a trial for 40% reduction, it will also always have a negative small sample size. But what happens is generally the effect sizes are only in 15 or 20%. A good drug will have 15 or 20% risk reduction. So the trials end up being underpowered, and when they are inconclusive, they are branded as negative, right? So one way is to use continuous measures, right? Or you can also call surrogate markers, but they are looked down upon. But when the primary trial is negative, you look at secondary outcomes and you do a larger trial on that. And other ways to collaborate rather than the publish or perish culture, or many people doing researches individually, which has led to a crisis of the sort. So that is what I meant. Mm-hmm. And also one commonly misunderstood thing is underpowered trials can occasionally lead to think about a border of India and Pakistan, and there is a small difference of a person is standing, jumping wildly between the two and is standing on side of India. So, okay, most of the time it will land up, but sometimes it will land up massively on the side of Pakistan because his standard error will be high, right? So so occasionally 5 in 100 studies, you will be having a inflated effect size, right? That is what is happening in nutritional research a lot, right? So you get these inflated
Right.
effect sizes. That is called M error, type M error, magnitude errors. Yes.
Now, there are certain trials where you feel it is trending towards significance, but not quite significant, and you're always worried either it's because of the sample size that is small, it's underpowered, and so on. Are there pointers to trials where you look at the trial and then say that perhaps this is a trial that would definitely have gained significance if we had larger numbers, and then can you actually recruit, as you said, in collaboration and try to get this into significance? Does that matter? On the other hand, you have other trials where large numbers are really large and therefore you land up with significance, but like you said, they are not clinically important. So is it just that the numbers push a trial towards significance? Is that important? How does that play out?
What the first question we need to ask is what happens if primary outcome is negative, right? And what happens if primary outcome
Hmm.
is positive? Now, if you one thing I look at if primary outcome is negative, where this or it just escaped significance, is what were the secondary results of the secondary endpoints, right?
Hmm.
Okay, if they are positive, then my gut feeling is strengthened, right? That the trial might be works, right? Trial might be working. And if only it could have been not powered with a fixed sample size. By the way, people generally nowadays use group sequential designs, so they can extend the sample size is variable, but sometimes it is not done. Frequently in India, we have fixed sample size calculations. So what happens is you have to look at secondary outcomes, and you can get a sense of that. There's a beautiful, review article in NAJM. What if the primary outcome fails by Stuart Pocock, who is a trialist, and you should read that. There are other points as well
Hmm.
regarding clinical trials being significant, but they are not, clinically significant. That is very apparent on
Right.
the effect size, right? Okay, your clinical
Right.
difference, okay, it would be 5 to 8%. Then you can spot it and tell them. If you want a number, give me a number, brother. Then I would advise you to go by base factor, because base factor would give an evidence for null hypothesis, even if the difference is statistically significant, right? Because you assume that effect size would be bigger, but effect size is really coming out to be smaller. So base factor accounts that if you intend to do a hypothesis testing. Yes.
Right. I think we should end there. I am going to ask the attendees again if they have any questions that they could type out, or questions that they would want to ask on their mics. And if they do, can they raise their hand, please? And if I don't have any questions from the audience, it is my duty to thank Dr. Anupam Kumar Singh for his excellent talk, and uh, thank you for enriching us and enlightening us about the use of statistics in medicine and nephrology. And I hope to put what I've gained in this talk to use. And I hope to meet you sometime, Dr. Anupam, when I'm in Delhi.
Great.
Thank you, and bye-bye.
Thank you. Bye bye.